Nearly 3 decades ago, amidst the breathtaking vastness of the Sahara Desert in southwestern Egypt, a seemingly ordinary morning turned into an electrifying expedition that fascinated scientists worldwide, igniting their curiosity and setting their imaginations ablaze. Now, picture yourself wandering alone through the endless dunes of the Sahara Desert. Each step you take is filled with intrigue, as if the sand beneath your feet holds a hidden message from the universe itself. Suddenly, your eyes catch a glimmer within the monotonous landscape. At first glance, it seems to be a commonplace stone, inconspicuous and forgotten by time. What is it that distinguishes this stone and renders it remarkable? Hidden within the depths of its average exterior, what mysteries could this rock hold? Our story for today begins in 1996 when Aly Barakat, an Egyptian geologist, was collecting samples in the remote region of southwestern Egypt. Barakat stumbled upon a small stone, about the size of a pebble, appearing to be different from the surrounding rocks. Driven by his boundless interest and determination, he decided to take it back to his laboratory for further analysis. It was at this pivotal moment that the various elusive pieces of the puzzle started falling into place. Named after the ancient mathematician and philosopher Hypatia of Alexandria, the Hypatia stone was unlike anything else Barakat had seen before. But where did it come from? Well, the answer lies in its notable composition that sets it apart from other natural objects, both terrestrial and extraterrestrial. Extensive research was conducted on the Hypatia stone to solve its mystery and gain insight into its extraordinary nature. One striking feature is its lack of chondrules. Chondrules are small, round grains that are typically found in abundance in most primitive and metallic meteorites. Chondrules are thought to have formed as molten droplets in the solar nebula, the cloud of gas and dust from which the solar system originated. These findings hold significance for understanding the events that took place during the formation of the early solar system, as well as imply an alternative origin and formation process. Another intriguing aspect is the unusual mineralogy. The Hypatia stone is composed of a complex assembly of minerals, including both known and unknown components. The known minerals present in the Hypatia stone include various types of silicates, such as olivine, pyroxene, and plagioclase feldspar. However, what makes the Hypatia stone special are its unique and exotic components. It contains minerals that have not been identified in any other known meteorite or terrestrial rock. These are characterized by their unusual chemistry and crystal structure. Some of the mysterious minerals found in the Hypatia stone are aluminum and titanium-rich compounds, as well as nanodiamonds. This stone contains silicon carbide and spinel as well. The isotopic analysis of the Hypatia stone has revealed some interesting findings. One study published in 2018, led by a team of researchers from the University of Johannesburg, reported that the isotopic composition of the Hypatia stone is highly unusual and distinct from known terrestrial and extraterrestrial materials. Specifically, the study found that the isotopic ratios of oxygen and nitrogen in the stone differ significantly from those present in any identified primitive or metallic meteorite. This suggests that the Hypatia stone may have originated from a previously unknown body in the solar system or even from outside the solar system. To delve deeper into this mystery, scientists have thoroughly examined the elemental composition of the Hypatia stone. Results have revealed that the stone consists of two distinct structures known as matrices. The first matrix is bimodal and carbonaceous, while the second matrix exhibits a more complex compositional pattern. These matrices hold crucial evidence that can help us understand the origins and formation of the stone. The first matrix is described as bimodal, indicating the presence of two different compositions within the stone. It's like two cosmic brushstrokes converging to create a charming contrast. This bimodal characteristic makes the Hypatia stone exceptional and stimulating for scientific study. Being also carbonaceous, this matrix contains a significant amount of carbon. Carbon is an essential element for life on Earth and plays a crucial role in shaping the properties of the Hypatia stone. Its presence imparts distinct qualities of the stone, contributing to its enigmatic allure. The second matrix of the Hypatia stone exhibits a complex compositional pattern, indicating an interplay of various elements and compounds. Through the use of ultra-sensitive X-ray emission analysis, scientists have identified an astonishing array of 15 different chemical elements within this matrix. What's truly astonishing is that the pattern of elemental concentration in this matrix is unlike anything observed previously. The scarcity of silicon and manganese, combined with the abundance of iron, distinguish the Hypatia stone from other carbonaceous chondrites. This unique and complex combination of matrices constituting the Hypatia stone highlights its intricate and uncommon characteristics, which prompts further investigations and raises intriguing questions about the cosmic events that led to its creation. How did the Hypatia stone acquire such a distinct elemental composition? What cataclysmic extraterrestrial events played a role in shaping its extraordinary properties? One popular theory proposes that the Hypatia stone originated from a specific type of supernova known as Type 1a supernova. This is a sort of stellar explosion that occurs in binary star systems where one of the stars is a white dwarf. But what's a white dwarf? White dwarfs are remnants of low-mass stars that have exhausted all their central nuclear fuel, lost their outer layers, and collapsed under their own gravity, becoming extremely dense objects. In a binary system, if the other star is close enough and evolves to become a red giant, it can transfer its mass onto the white dwarf through a process known as accretion. As materials from this companion star accumulate on the surface of the white dwarf, it increases the mass of the white dwarf beyond a critical threshold called the Chandrasekhar limit, which is about 1.4 times the mass of the Sun. Can you believe that? Wait, we're not done yet. When the white dwarf reaches this critical mass, its core becomes hot and dense enough to ignite a runaway nuclear fusion reaction. The fusion of carbon and oxygen in the core releases an enormous amount of energy, causing the white dwarf to explode in a brilliant display known as the Type 1a supernova. This cataclysmic explosion scatters the star's matter and byproducts throughout space. The Hypatia stone is likely to have been formed from the debris of a Type 1a supernova. In fact, the composition of the Hypatia stone, particularly its high iron content, matches what we would expect from the remnants of such a cosmic event. The presence of mysterious elements within the stone's second matrix challenges the supernova hypothesis. In other words, not all components detected within the second matrix correspond to the expected chemical signatures of a Type 1a supernova. The Hypatia stone contains aluminum, phosphorus, chlorine, potassium, copper, and zinc, which are present in concentrations 10 to 100 times higher than expected for a Type 1a supernova. This discrepancy raises further inquiries and suggests the possible existence of additional factors or unknown conditions that influence the stone's formation. While there is still mystery surrounding the existence of the Hypatia stone, we do know that it was formed in an environment colder than liquid nitrogen, with temperatures around -196 degrees Celsius. We also know that it originated from beyond the asteroid belt, which is where most of the meteorites came from. The Hypatia stone instead came from the Kuiper belt. Although the samples in hand were not a perfect match for a Type 1a supernova, the supernova theory remains the most plausible explanation for the creation of such extraterrestrial stone. What mysterious forces shaped this stone and what celestial magic intertwined to create the riddle we now seek to decipher? With each new discovery, we move one step closer to comprehending the celestial events that gave birth to this cosmic wanderer and deposited it upon the desert sands of Egypt. By further examining the structure of the Hypatia stone, we are expecting to gather more crucial evidence supporting the notion of its extraterrestrial origin. The composition of the Hypatia stone is truly impressive, isn't it? What other secrets do you think the stone hides? Please feel free to share your thoughts in the comments section below. Hope you enjoyed this video. Thanks for joining us and stay tuned for what's coming next.